You want to get started?
Sure. All right. Well, welcome back. Hope you enjoyed your lunch. I'm very happy to have Kevin give the last part of his winter school lecture series, but that's not the end of his lecture series. Please do tune in to his lectures that will run throughout the semester if you can. If you cannot, they will be recorded and posted on the Fields website. But in any case, Kevin, take it away. Thank you.
Okay, thanks, Leo. Okay, so in the previous two lectures, the first one was work from about 4 or 5 years ago. The second one was work from 1 or 2 years ago, and this is from like last week. So this is our building on the others. All right, so here's I presented a preliminary version of this talk. Actually, I guess this is the 6-month anniversary of the birthday of Olivier Lafitte, and so it can still be his birthday talk. He played a big role in this. And okay, so some preliminary. We are interested in time asymptotic stability, so long time behavior of shock waves. And not only viscous shock waves, but shock waves that might have discontinuities. So that's surprising. And it should make you notice maybe the title had Kreiss symmetrizers. That's a big part of the MIDA theory of inviscid shock stability in multi-D. And that's natural because if you have discontinuities, you might expect to encounter something like what MIDA did. Of course, MIDA is showing, for all the reasons we've seen in the other lectures on singularity formation in short time, the development for conservation laws is only a well-posenness or short time kind of stability result. And we want now to go to long time. It seems strange, but of course there's a secret fine print. We're doing it for relaxation system. That means it's not conservation laws, but there are some balancing terms that can give you extra decay, some damping terms. And okay, so that's what's going to make it possible. All right, so I mentioned that, and a key point and kind of the reason this is dedicated to Olivier is Mark Williams, Olivier Lafitte, and I just devoted one summer just for no particular reason. We wanted to read a paper of J.J. Erpenbeck on detonations, kind of from the archives of Los Alamos that Mark had found, this 100-page paper that just really wasn't sure what it was. And he was so far ahead of his time. We read about this, and it's high-frequency instabilities for detonations. And those ideas proved to be exactly what's needed for what's going on here. And if we had not done this LARC, I wouldn't have recognized it. If not for Olivier, I wouldn't have seen the Airy functions hidden in there or anything. So it's kind of fun. All right, so here's what we're going to be looking at: hyperbolic, quasi-linear first-order balance laws in multi-D. And the examples are, if the source term little r is 0, that's conservation laws. We've been talking a lot about that. And for a relaxation system, we have the real part of the spectrum of the Jacobian of r should be less than or equal to 0. And it should be strictly negative off of its, well, it would be strictly negative off of its kernel. The kernel should be of a constant multiplicity. Okay, so we know from conservation laws we have formation of singularities in finite time. But we also know for relaxation systems near constant solutions. We know by the work of the Japanese school, there are a few names, but Kawashima is the well-known kind of description of this approach, that we have global existence of smooth solutions. Singularities do not form if you have to start with small data. So that's important. And okay, so a key element in all this, somewhat abstracted, I'm putting it in my own words here, is what I call a nonlinear damping estimate. And this means you find an energy, calligraphic E, such that its time derivative is bounded by negative eta times E itself, plus a big constant times the L2 norm. And here, this energy should be it should be equivalent to an HS norm with S perhaps high. What that means is you have slaved high derivatives to low derivatives. It's exponentially slaved. And right. Okay. And so, right. But this is not how I like to use it. I like to integrate that into a Grunwald type inequality, and you can write it like this: that the H passing through E and then going back to the HS norm, you have that the HS norm at time t is bounded by an exponential multiple, exponentially small multiple of the initial data in HS plus a memory term, exponential memory term against the L2 norm. So if you have a nonlinear iteration, you have an estimate, probably some time algebraic or time exponential bound on this L2 in here. And it doesn't matter if you put in any algebraic norm here and integrate it, you'll see that it's the same as evaluating at the top T. It basically says that the HS norm is bounded by exponential multiple of the data, exponentially small multiple, plus the L2 norm at time capital T. That for purposes of iteration, it does that. And why is this important? Well, when you do linear bounds, you often lose derivatives because it doesn't take care of nonlinear structure that is sometimes, for example, even think of Friedrich's symmetrizer theory. You do energy estimates and you lose no derivatives. But if you do just a linearized estimate, you will lose one derivative. That's standard.
Big T minus small t.
Oh, minus small t. Sorry, that's a typo. Yes, yes, minus small t. Yeah. So yeah. So it's basically concentrating at big T. Right. Yeah. So and if you write it this way, it somewhat simplifies the old proofs for constant solutions. It looks nicer. It's very easy to use in this way. It's really the same, but repackaged a little. Okay.
This way it's alpha, the exponential.
Yeah, and sometimes, okay, for the nearly constant solution, you don't need any weight. You just use Sobolev spaces. Something that I have found useful we want to treat large amplitude waves. That's kind of been the whole game in my work, is trying to go away from constant solutions and careful normal forms and things, and just use the spectral information alone on the linearized operator, plus some high frequency estimate like this. Yeah. Okay. So Gilles was just talking about the Lummer-Phillips principle that says if you can find a nice coercive energy, then you get a contractive semigroup. So in my mind, this is a little bit like that, because when you do have an energy estimate like the above, that's like being coercive in this capital calligraphic E weighted norm. But you don't get, of course, and it would be even better, it would be more than contractive, it would be exponentially decaying at rate negative eta if you had, I mean, that's another application of Lummer-Phillips, but we don't quite have Lummer-Phillips because we have this term. So it's kind of like, it's kind of restricted to high frequencies in a way. Okay, and so it doesn't give you as much, but you don't need as much. That bound is a lot easier to get. Yeah, just have a look again. There are all sorts of commutator terms that happen in energy estimates when you do the high frequencies, and you can collect them all into this L2 term. So you kind of don't worry too much about them. And the principal parts are mostly all that matter. So that's a big help. Okay. So this direction, this is something that I've wondered about since about 2003. And when I was thinking about these things. So if I have such a coercive estimate, I get a high frequency resolvent bound. So that's another good thing, because getting the high frequency linearized bounds is really tough often. This is the only linearized bound I need, and some inverse Laplace transform manipulations. And that's good enough to get exponential decay on the high frequency part of the linearized solution operator with loss of perhaps many derivatives, but finitely many. And so that's another thing. So I can use the same circle of ideas to, this simplifies the nonlinear term, the nonlinear linear estimates, but at the price of derivatives, which, however, do not cost me anything because I can gain them all back with this damping estimate. at a higher S. So it works very nicely. I'm not going to talk any more about that, though it's important in almost all the works, the stability works that I've done and in some other form, I would say, that others have done, not necessarily written like this. Okay, so this is very important, but the reverse is not true. What you would like is that whenever you have a good linearized high frequency bound, that you could find a nonlinear bound. That's the Lyapunov theory, right? You find a nice robust nonlinear bound whenever the linear estimates are good. You would like that. It's not always true. And here, this is not true for this type of estimate. Okay, so the whole purpose of this talk is to give a different sort of scheme or estimate that gives the same information as this, but doesn't suffer from that problem. That is basically nearly equivalent to the high frequency resolvent bound. But okay, before I do that, I'm going to borrow a trick from my old colleague and mentor, David Hoff. He used to do that in his talks and lectures, just to further go to hyper speed, I guess. But I don't have very much time, so instead of I prepared this on the board. So I want to show you just what this old style that I'm describing, just for reference, what does it look like? Okay, so and the good starting place is viscous conservation laws. So here's a viscous conservation law: dTW plus dx f of w equals dx squared w. So we've seen that plenty of times. Okay, first question: what's this? This is standing wave ODE in some community. Okay, so if that means I just cross out the time. That's the same as a shock wave just in its own coordinate system, in its own moving frame. If I do that, then it's just okay. Here's dx of w, f of w, and then dx squared is over here. I'm not going to bother to integrate it up. It's some kind of ODE. When you solve it, you get a nice smooth profile, and it exponentially approaches the end states. And all the derivatives are several derivatives are bounded, as many as f has, basically. Okay, so now we want to talk about, do singularities form in perturbations around those waves? So I'm going to linearize around the wave, and I'll throw out the nonlinear terms, because the basic ideas can already be seen here. In the linear form, I won't have to write as much. So here's the linear equation. So if we use the perturbation around the wave, we have dx of f, so that becomes a bar. A bar is the Jacobian of f at w bar of x. V, and then dx squared v, that's all there is. I want to do exactly the same things as we saw, the same starting point as in Kohlstocks, as in Fritz-John, et cetera. We want to differentiate and look at the differentiated equation. So z is the x derivative of v, and the equation looks very similar, of course. Now, what if I just take the simplest energy estimate you could imagine? So I'm going to denote the L2 norm just by single bar and the brackets for the L2 inner product. So here it is. The time derivative of L2 norm of z squared over 2 will just be z against the equation. The right-hand side of everything but time derivatives pushed onto the other side. Here they are. So it'll be just z against dx squared z and z against dx squared a bar v. Okay, so this is a school, so I can assign homework. So here's the homework. You just notice by parts that this first term is negative dxc squared. It's a good term. And all the rest can be put in order of dx z L, by Cauchy-Schwarz, it breaks like this. It's dxz against dxc and possibly some v's. And here's the homework, is show that you can subsume all this into, I'll give away half of this, so I'll keep negative 1/2 dxc squared, which I want for my damping, and then I can put everything else by a big constant times v squared. Okay, it's pretty standard. One part is just Young's inequality that breaks products into product of norm of f times norm of g is norm of f squared over 2c plus c norm of g squared. Many are familiar with that, but maybe less familiar with the Sobolev interpolation, which is actually proved by Young's inequality in Fourier space, that I can control the L2 norm of dx by a big constant times the L2 norm of f, plus a very small constant times the second derivative, the L2 norm of the second derivative. And put those together, you get this. Okay, so that's homework A. Homework B is, okay, now do the same estimate on V itself, add them together. So I'll define the script E to be norm of dx squared V, that's Z squared over 2 plus norm of V squared over 2. And that will satisfy a damping estimate, as I meant to have it up on the screen. So let's put it back. Yeah, damping estimate as at the top of the screen. So that's not too bad, right? It's a very soft sort of argument. And in fact, we're giving up lots of information we know about parabolicity and smoothing and all that. We're not using any of that. We just what we're keeping is what we would have for degenerate viscosity and relaxation, which is only this, not smoothing. Okay, so is that okay for everybody? Now I want to show you why is the relaxation case a little harder or different. It has some new issues. Okay, so now same equation, but on the right-hand side, I have this source term, R. The standing wave ODE becomes a little interesting. Now I have A of W bar times W bar prime equals R of W bar. This is very nice if A is invertible, but as we saw in geostock, for example, but, sometimes these things are not invertible, and then you have real issues. I'm going to stick to the case here where it is invertible, and that all the relaxation shocks I showed you in the previous talks, they have that property. So I'm somewhat justified, but there are other problems like roll waves or implosions, and there are plenty of problems. They seem to be coming from all sides these days, these singular ODE and their associated spectral issues. It's really important, but I'm not doing it here. This is just a start. Okay, differentiated, the linearized equation looks very similar, but now I've put the Jacobian of R as an E, capital E bar. The differentiated equation here in Z is the derivative, x derivative of V. Now, I try the same energy estimate. Okay, and I get Z against the equation. I have a good term, Z against E bar Z, and I have I don't know what kind of term, maybe good, maybe bad. I've split apart now this term into two parts. I'm keeping only the part with where the dx falls on the V. And there are other terms, but they're already okay. They're order of V times Z. We've already seen how to handle those. But this is like the second term in Xia's energy estimate. It's exactly the same. That was a good setup, so thank you. So that could be very significant. For small waves, it's not significant. If I have small amplitude waves, then the x derivative of the matrix A, it depends on if the derivative of W bar is small, this is small. And this term, we presume is going to have a good sign. That's an assumption. That was an assumption at the equilibria. If it's a small wave, everything's near equilibria, and this will still have a good sign. So this will be a strictly coercive term. This will be a small term. These are harmless to begin with. We're done. We get damping again. But when you have, oh, sorry, I forgot to do the, yeah, you have to, of course, you have to make one more assumption here. I need to assume that A is symmetric, which is often the case, but not always. If I assume it's symmetric, as is that is true for it's symmetrizable, basically. So Saint-Venant has that property, then I get this. So that's where the dxa came from. I forgot to mention that. Okay, but if it's a large wave, this could be as big, we don't know how big it is. It could easily overwhelm the good term. And not only that, for large waves, well, this term is good near the end states, but the end states might be far from other points on the profile. There's nothing that says that this is a good sign everywhere. So, oh, and finally, I drew this nice picture here, reminding you of some of the waves we've seen. The large amplitude ones could be smooth. They can also have discontinuities. So that's another issue that's different. Now what are we going to do? Well, here's what should give hope. is that let's just do one scalar, let's do a scalar model. That's the ultimate symmetric guy. Okay, so now capital A is replaced by little a, everything's symmetric. And here are our assumptions. A is, so this is one thing we do keep. A is bounded away from 0. The speed is always non-characteristic because we assumed that at the beginning. We assumed that the determinant of the matrix never vanished. So this has a sign. So I'm going to just look now at method of characteristics and think about formation of singularities. These waves are moving from left to right. Okay, there's a region where everything's good. That's for large values of x. So out here and out here, everything's good. The sign of E is good. The derivative of A is small because it's exponentially approaching limits. Everything's fine for the estimate. We only have one bad region, but the bad region is finite. We spend a finite amount of time in here. So if you're doing this by method of characteristics, this is just Z dot, right? And we have good term, and we have a term that doesn't matter anymore. Right. So this term may be bad in the intermediate finite zone, but it doesn't matter. We'll just integrate it up to get a constant. And after that, we exponentially decay. So we see that don't exponentially decay, rather we're slave to order V. We're slave to the L infinity norm. So we would get kind of, in method of characteristics, we'd get sort of a nonlinear damping, but in the L infinity norm. And you would see it could not blow up. You won't get singularities. You could even stick in a discontinuity in here with a good decent boundary condition, still no problem. Easy to fix. You put a weight, you put a very small weight on the right-hand side. So whatever comes out gets shrunk, and then it starts decaying again. Okay, so that's what gives us hope we might be able to do it. But remember, I'm really interested in multi-D. So, and there you don't have, you will lose this because as Maida shows, and as people know well, in multi-D you can have glancing modes. These characteristics can turn back around for certain frequencies, certain transverse frequencies, and so you won't have this picture. Okay, so all right, so oh, sorry, what happened? There we go. Okay, so what are we gonna do instead? I'm gonna say we make the same change of coordinates I just did. Sorry, we've got the linearized equations. Okay, now we make a time-weighted change of variables. So e to the gamma t v, and then we Fourier transform in all directions, time and everything but x1. And that's the same as taking the Fourier transform in x2 through xd, d being the dimension, and the Laplace transform in time. So it gives us a resolvent equation. And with lambda is gamma, that just came from the change of coordinates, and I tau, which came from the Fourier transform in time. And the price I'm paying is I have to take time from negative infinity to infinity. So it's not good for initial data. It's good for zero initial data and forcing when you do this kind of thing. And this is what's done all the time in the Maida theory and descendants. Okay, so also, I thought, even though in the title I'm talking about pseudo-differential damping, and actually what we use is the paralinear calculus of Monine. This is all I'm going to say about it. If you instead look at paralinearized and got operator symbols, you'd get something that looks exactly like this. And so I'm going to do estimates on the actual resolvent equation. But the rule is I have to do estimates that you can do using the paradifferential calculus, and there are acceptable commutator estimates. And okay, this is by now pretty well known. This is what Olivier Guess, Mark Williams, Guy Mativier, and I did a lot of work on. So, okay, so what we're going to do is, and this is exactly what's done in the Maida theory, and well, plenty of work. So what would you do if you had, let's see, so we're going to look for an estimate that looks like the damping estimate, but at the resolvent level. So we want, so here, I should go back and just say one thing. So, yes.
You have the preferred direction here, X1?
Yes, X1 is the direction of the shock. So it's the direction in which, this is a planar shock that I want to look at, or something close to it. I want to, yeah, I should have said it. These are the waves that we were pictured in the second talk. They're constant in X2 through XD, varying only in X1, and that's the game. And I should say also, here's my notation. So if I'm talking about, this is the resolvent equation, but the resolvent operator would be applied to F and give V. So if I want to talk about a resolvent bound, it means the norm of V bounded by the norm of F. That would be bounded resolvent. Okay, and so that's why here you don't see any linearized operator, you just say V and F. Okay, so what I want is that the HS norm be bounded by a constant times the FHS norm, but then a possibly very big constant times the L2 norm of V. And that's kind of vaguely analogous to what we did before, but at the resolvent level. And here I wrote on H hat, it just means I want to do the Fourier transform version of that, of the HS norm. Okay, so if V and F are supported just between 0 and capital T, then this works out fine. Because remember, I have to integrate T, I have to take T from negative infinity to plus infinity, but if it's only supported there, that's fine. And then I get, by Parsifal's inequality, I get immediately something that looks like the time integrated Grunwald version that I like. The right-hand side is the same. The left-hand side is different now. The left-hand side is a memory, it's the same exponential averaging of V. So it's basically supported at capital T, but it has some earlier terms. This is also fine for a nonlinear iteration, it's just fine. It does not allow for initial data, but by some kind of standard maneuvers, you can always put the initial data into a forcing, and that's not a problem. So that's done a lot by Kreiss, and this reminds me also of some work of Jeffrey Rausch. Okay, so if we can get this kind of norm, I mean this kind of estimate, then we can, whoops, we can do the rest. Okay, so first observation. This is really trivial, but I want to know that whenever I have a high frequency resolvent estimate, that's good. And what would good mean? It would mean that I can extend the resolvent past the imaginary axis into the negative real part side where you have exponential damping, but only for high frequencies. So, yeah, so that would be this. The HS norm would be simply bounded by, the HS norm of V would simply be bounded by the HS norm of F if real part of lambda, which is gamma star, and gamma star is less than 0, and for high frequencies, for both lambda and xi big. Yeah.
Is this idea somehow similar to the what is this geometric control condition idea by the micromolecular analysts? So basically, they're saying that you have like a damping region, and then this.
Oh, that may be so. Yeah, there are some, or something called elliptic region. Wait, yeah, okay. That is probably so, but I'm not familiar with that literature. So, okay, but this is what you get from linear analysis, like some WKB, or who knows, or maybe maximally dissipative operators. Who knows? You get something up at high frequencies, and then now you're very encouraged, and you want to finish the nonlinear analysis. Can I get a nonlinear damping estimate? Then, and this says, okay, I don't know about the nonlinear analysis, but at the linear level, these are equivalent. So this damping estimate I wrote above is equivalent to this damping estimate. Well, they're almost the same, aren't they? The top one just has an extra L2 term, but it's also supposed to hold everywhere for all lambda with real part equals lambda star, possibly small frequency, not only the high frequency, but that's not very hard to see. So we just noticed that if you're bounded, the principal term is A1 dxv. And the equation says it's bounded by V plus F. So, if A1 is invertible, which I'm assuming, then I have that the H1 norm is bounded by the L2 norm. So that's that says this always holds, because I just using the VL2 term alone. And if I have large, let's see, yes. If I have high frequencies, so now it's just a question of equivalence at high frequencies of these two things. And the only difference is there's an extra term here. So I have to show that extra term is small, but that extra term, of course, is small because if C is much bigger than 1, well, then there's a C squared out in front of the, and C is big out in front of the HS, sorry, a C to the S in front of the HS norm. So the L2 norm is like 1 over C to the S times the HS norm, trivially. And if lambda is high, then we go to the resolvent equation again, and we see that the L2 term can be absorbed. So we see that the L2 norm is much smaller. Why? Well, we have a lambda times V. On the right-hand side, we have only good terms, plus, and yeah. And is that what I want to say? Yes, yes. So the right-hand side is bounded by the H1 norm. The left-hand side has lambda times L2 norm. So L2 norm is H1 over lambda, much smaller than lambda. So this L2 term can be absorbed for high frequencies. So it turns out it's almost a tautology, not hard.
So sorry, you will use this proposition if you have the second part of the statement, then you will have to estimate.
Yes, that's ultimately, but really though, this is only kind of a remark. This is what got me very excited about the idea, because for the other kind of estimate, you could have a good resolvent bound, and you didn't get that kind of Neumann-Phillips type pointwise in time estimate. It just, they aren't equivalent. So that means there's really no hope to generally, to always be able to do that. And in fact, I have some examples where it seems you can't do that. But this one, at least at the linear level, you always can. Now, nonlinear level is different though. We have to, but this gives hope, that's all. This is actually unrelated to the rest, and it's really a trivial observation, but it's kind of motivating. Okay, so
because this proposition applies to the question about earlier A1.
yes, oh, it would, yeah. So there's already something there, yeah. So for instance, if I want to get well, I can say more though. Let me say more. But from this same proof also shows us that, I mean, whenever I have this estimate, I could just as well have gotten the other one, and vice versa. They're really, because this one always holds for bounded frequencies, and so it's really only about high frequencies. So it's good and bad news. It gives optimism, but it doesn't give any clue how to get the bound, because they're really the same. They're the same bound. So you still have to work to get it. So, yeah. So the question is, how do we get the high frequency damping, which is the same as getting just high frequency. All right, but so now I want to use the Kreiss method that might have used to study discontinuous waves, because there will be discontinuous waves sometimes, but it turns out even for smooth waves, you need this. And that's the observation of Erfenbach, really. But okay, so I'm going to give you variable coefficient symmetrizer. So in the MIDA case, shocks are constant away from the discontinuity. So you can use a constant symmetrizer. But here you need to use a variable coefficient symmetrizer because the profiles are varying away from the shock. And so you have to take a family, so it's x to s of x. S is symmetric, and it has this, and bounded, and it has this property. Twice real part of s times g, oh, I forgot to say, start by writing the resolvent equation in this abstract form. dxv, I'm going to drop the x1 now. This is really about ODE. dxv equals g of xv plus f, so f is the forcing. I want to bound v by f. This says if I have, if the symmetrizer satisfies 2 real part of s g plus dxs is coercive, is bounded from below by 2 theta, then I have the estimate I want. And the exact form of the constants is not important. I bound v by f. That's all that's in. I get a resolvent bound. And the proof is, it's dead simple. You just start with the identity that dx of v sv, because s is symmetric, is equal to this right-hand side I've written, twice the real part of v s dxv plus v dx sv. And I use that dxv is gv plus f. So I use the equation now and plug it in. And here's what I get. 0 is equal to this piece plus this piece. Okay, now, and that is, yes. So this one is coercive, theta v squared. The next one, I just use Cauchy-Schwarz. Now I divide out of v, norm of v, done. So it's all set up perfectly. And then if you have a discontinuity, there's another condition, but we're going to avoid that here. So this, if we can construct these things, great, we're done. Okay, so I'll give you a case that's easy to construct. And the case is, so let's see. But okay, so first thing, we're looking at high frequencies. And this is very much the same as what Kreiss does. So at high frequencies, we'll write the equations. Okay, here are the, I'm going to put the A1 inverse over on the other side. This is the, this is now dxv equals gv plus f. All right, but this is actually a high, it's a semi-classical limit problem because lambda and xi are together are large. So I have this principal term, and then I have some corrector. And I want estimates. Okay, so there's an easy case. The easy case is if this principal part, well, if the whole thing has a spectral gap. So this is very big and neutral, right? It's basically hyperbolic. So it should have kind of imaginary eigenvalues, we think. In 1D it would, always. This one is real, but we think it has kind of a good sign, at least out near infinity, or good enough to help us. Okay, so we want to show that somehow we have a spectral gap of order 1, even for very big frequencies. What if we have that? Okay, well, in the constant coefficient case, Kreiss observes whenever you have a spectral gap, you just use a Lyapunov lemma. First, you project onto stable and unstable parts, and then you look for basically a Lyapunov function on each separate part, and you easily get a symmetrizer. Here, we'll do the same thing, but with exponential dichotomies, because this is a variable coefficient ODE, not constant coefficient, and so you need to work a little harder. Okay, so let's see how you do this. It's actually not very hard, except for tech is hard. We have dx, that's supposed to be dx of v equals gv. All right, so there's no forcing because I just want to look for an exponential dichotomy here. Okay, so, and construct a symmetrizer. So this is just about the structure of G and the differential equation. So suppose I have an exponential dichotomy. That means I have smooth, uniformly bounded projectors, P plus and minus, onto the stable and unstable subspaces of the flow of this ODE, which I'll call sigma plus and minus. Okay, and for V in sigma plus, I have the uniform estimate. V of x is less than or equal to a big constant times e to the minus theta x minus y, V of y for x greater than y. So it's exponentially decaying in forward time on the plus, sigma plus. Okay, so this is very much like, this is like a bounded semi-group type estimate as opposed to contractive. And what I'd like to do, I want to find a norm where it's contractive. Same business. Okay, but so what I do is first, I notice, okay, the existence of these dichotomies means that I can block diagonalize the system into two parts, V plus and V minus, the growing and the decaying parts. So that's automatic here. And we're going to seek S in a block diagonal form, naturally, to work with this. And all I want is, let's focus on the G minus part. I want the 2 times the real part of S minus G minus plus dx S minus bounded by negative theta. And I'll do a symmetric construction for S plus. And here's how you do it.
What is the role of the P?
A little p.
In the first equation.
Oh, sorry. P is parameters. Just to say we have frequency. In reality, we have frequencies as our parameters. And possibly there could be other model parameters. It's, yeah, almost nothing here. Right. It's just to say that actually everything would be uniform. If it were uniform, smooth in P, we need that for the power differential stuff. So we need to keep track that things are uniform. And I'm just saying it would still be nicely, this construction is nicely uniform as long as the exponential dichotomies are uniform. So that's part of the assumption. They have to be smooth in all parameters. And otherwise you don't get the power differential result. Okay, and then, so what we want is a Lyapunov function, but non-autonomous, that takes, let's see. And we'll define it like this. It's basically V transpose against S V minus. And we want that the x1 of V, capital V of this Lyapunov function is less than or equal to negative theta V minus squared. That's the same. And then we'll define, and how can we get this? It's the same as you would do to change a non-contractive estimate into a contractive one. You define little s to be the integral of, okay, capital S, that might be bad notation to go with little s, but this is the solution operator from x to x1, from x1 to x, sorry. And this is from x1 to x. And we just take the, we take the square. And that means that V of V minus is actually the integral from x1 up to infinity of little v of x squared. Because the solution operator just takes V at x1 up to V at x. Okay, and now if we differentiate that, we can see trivially, it's the value, it's negative little v at x1 squared. And that's coercive. So that's an old trick. It's a really good one. And that's how you can do it. So you can construct a symmetrizer in this way, just like Lyapunov theory for ODE, non-autonomous ODE. Okay, so a corollary. This is a great corollary now, and this will answer the question over on the lower right board there. What should we do in general? Well, if you have in the 1D case, if A1 is strictly hyperbolic, so it has separated modes, characteristics, and the determinant is always non-zero. So not only are these eigenvalues separated, they're different from zero, so they keep their signs. Plus, high frequency damping at the end states. So this is dissipation. It's a dissipation condition that some people usually call it that. Or anyway, this is the Fourier symbol of the operator, and we need that the spectrum be less than or equal to negative theta, less than 0, if we have sufficiently large Fourier frequency C1. That's what is needed for high frequency stability of constant solutions. And it's just a linear algebraic computation. Okay, and then, okay, so now I claim if that's true, then everything in sight is equivalent. Nonlinear damping, existence of exponential dichotomies, and high frequency damping at end states, all those are equivalent to what's in red, this linear algebraic condition. So life is great. And it's just what you would have to check anyway to make sure the end states are good. Let's see how we time here. Okay, I think I have time. Okay, the main direction. Okay, unfortunately, I have a typo there. Okay, so I'm gonna go to the board again. So in my defense, these slides were sent here substantially before the talk. But okay, so the very first line should be, well, we want to look at actually, let's first look at that condition. Okay, so I first want to unpack the red condition. What does it mean for high frequencies? Well, without loss of generality, let's take this to be alpha 1 through alpha n 0, 0. So diagonal, I can take A to be diagonal. And then I have certain diagonal, let's see, these are E1 through En, I think is what no, I wrote beta n. Okay, so, all right. And there's an IC here. So if I divide the whole thing by IC, then the spectra are IC times this plus 1 over IC times this. It's now a matrix perturbation problem. And I know, and this is the small perturbation, I know when I perturb a diagonal matrix, the next order perturbation is just the diagonal entries. So this is the spectra are equal to AJ, IC AJ plus beta J plus order of 1 over C. So this condition is beta J greater than or equal to theta greater than 0. It's just saying that these diagonal entries are positive. And that probably reminds you of the Kawashima kind of theory if you're familiar with it. Okay, but now what I wrote incorrectly is this is not, of course, this is not the symbol for the ODE. The ODE is dx v equals g v, and g is equal to a inverse lambda plus, or negative lambda plus e. Let's see, I said one thing wrong here. Let's see. No, that's right. So, so beta, it's actually, I'm sorry, the dissipativity is negative. The betas are less than or equal. Beta less than 0. Because dissipativity requires negativity. Okay, now I get this, and I want to look at the spectrum of G. So I'm saying that the spectra of G will have a spectral gap. So here, if I have dissipativity here, I'll get a spectral gap here. Well, it's actually the same thing. This is alpha 1 through alpha n 0, 0 inverse, so 1 over alphas. And then we have negative lambda, and then plus beta 1 through beta n. Some other things, but once again, lambda is large, so this is just a matrix perturbation from diagonal. And again, I can throw out the diagonal terms, and what I get is negative beta j over alpha j for my spectra, for my real part. Yeah, that's what yeah, so I'm going to look at the real part of the spectra. The real part is negative beta j over alpha j. That will it'll depend only on the sign of alpha j. Okay, so that gives me a spectral gap. And once I have a spectral gap, well, again, so here I can use well-known methods, basically WKB, but I prefer to think of it going way back to Levinson's ODE works, just repeated diagonalization of the equations, because you can approximately diagonalize this. You diagonalize the principal part, which is the lambda A inverse part, and you have a small error on the off diagonal. But we know that then we can remove those off diagonals by an even smaller, a very small perturbation of the identity of order 1 over lambda, and keep going as many times as we like to make that small. And so long as we have an exponential dichotomy for the principal part, we'll be fine. And we do, because this is good at plus infinity and minus infinity. It's possibly bad on some bounded domain, but exactly like the picture I drew at the beginning, that won't hurt for an exponential dichotomy. Because it's just bounded, and you can accumulate as big a constant as you want. Okay, so then we have an exponential dichotomy. So red sign gives exponential dichotomy, gives nonlinear damping, and we're done. Okay, so that gives, for 1D, we're finished. Okay, so, but that can't be all of it, because 1D isn't everything. And we already know from Kreiss theory, constant coefficients, that's an example of variable coefficient, just a trivial one. And we know for constant coefficients that definitely you can't always diagonalize the G. In fact, there can occur Jordan blocks when you reach bad frequencies, which are called glancing frequencies. And at any Jordan block you lose, you're not going to have a smooth exponential dichotomy because projectors blow up. So even for the constant coefficient case, we know that's not true. But maybe you could somehow avoid that. What about the variable coefficient cases we see for Saint-Venant? And we have for Saint-Venant, you're able to compute the profiles explicitly and calculate everything. Okay, so what you get is this. So instead of bad frequencies, you get bad X points. So for very many frequencies, there's some X where the equations are bad because the model parameters are changing with X. So you're sweeping through a variety of models, and it's very unlikely that your frequencies that you're fixed at, that they're going to be good for all those different model parameters. And if you zero in around a Jordan block and expand it, this is what you get generically for G right here. So first I changed coordinates so that the principal part was a Jordan block when X equals 0. So I'm putting the singularity at 0, X equals 0. When X equals 0 and A of X, just think of X. So, okay, so then this would be just, and lambda equals 0 is also, I'm centering around that. At lambda equals 0 and X equals 0, we have a Jordan block. This lower left-hand entry vanishes. And this, what I've written, when I take A of X equals X, that's the Airy equation in first order form. And this is a classical turning point issue that you see in geometric optics. Okay, so could it somehow have an exponential dichotomy nonetheless? Because of the variable coefficients somehow, it's actually not even a sensible question, but you can easily answer it. Okay, you look at the eigenvalues, you compute them, here they are. From the eigenvalues, you get left and right bases, which are then, and so you can do an approximate diagonalization, and you can perform the Levinson repeated diagonalization. It's going to work if you're bounded away from 0. And the question is, how far away from 0 do you have to be to make it all work? It turns out it's exactly, the Airy scaling is X over H to the 2/3. And here H is 1 over the frequency, it's small. Okay, and so it turns out outside that Airy core, you can diagonalize everything. Okay, and you can find the projectors, but they're of size H to the, where'd they go? They're H to the minus 1/3, I guess the projectors are blowing up. Yeah. Okay, so, if you stay right at the edge of this core. So no good. Could there be symmetrizers? Well, yes, it turns out there's a really trivial symmetrizer. This is basically, I should have said, this is basically the problem with Kreiss frequencies, but I've substituted in variation in X for variation in the frequency, in the imaginary part of the frequency. I basically just swapped out two things. And if I then use exactly Kreiss symmetrizer, this is what it looks like. It's actually constant coefficient. Here's my S. Okay, it's 1 plus IH, 1 minus IH. So it has a symmetric part and a skew part of size H. H is small. And the real part of SG by direct computation is this. Okay, so we have gamma, which is the real part of lambda, times something which for A and tau and H small is small. So basically gamma, gamma. This is coercive of size gamma. It's what we wanted. Okay, so that's fine. You don't want to only construct symmetrizers in a small neighborhood of 0. You have to connect them up to other ones. But okay, so that can be done. That's all I'm going to say about that, because I wouldn't have time for that. But yes, so theorem, the best theorem at the moment says that if we just have one Airy type turning point at some finite value at infinity, and we take the critical frequencies, which are the principal part I tau, pure imaginary, and eta large, then we do have such a nonlinear damping estimate. Now the other frequencies actually have exponential dichotomies. So this is enough to give nonlinear stability of the smooth relaxation shocks that I showed you. And that's something that I've been wondering about, now for more than 20 years. How would you even start with that? So I'm very happy about this. On the other hand, the proof of this, it's very patched together. It feels like there should be something very systematic, like Kreiss theory is quite general and beautiful. And this one is kind of, I wouldn't call it beautiful other than it works. Yeah. So what else? I will mention, even in the, even in the 1D case, we still could get estimates, but we needed to assume all kinds of symmetrizability, all the Kawashima kind of conditions. That's actually, there are interesting cases where that's not true. And I have a recent paper with Matthias Strosinski on stability of relativistic viscous shocks. Those are actually relaxation shocks. They have causality. They can't have infinite propagation speed, and they don't have the Kawashima properties, and yet they're still stable. So that was pretty nice. And what else? Oh, yes, of course. When you have the singular ODE, when determinant of A can be 0, of course, there are many interesting applications there, and I think that's a really good direction. Okay, and I wish Olivier a happy 6 months after birthday.
Questions?